While we cannot directly observe black holes due to their nature of not emitting light, there's a vast amount of evidence supporting their existence, making them one of the most compelling predictions of Einstein's general theory of relativity. Here's a quick summary. Black holes are not cosmic vacuum cleaners, but they do have a hearty appetite for gas and dust. As this unfortunate matter spirals towards its doom, it gets superheated in a swirling disk called an accretion disk. This friction generates intense X-ray radiation, a beacon in the darkness that astronomers can detect from Earth, painting a picture of the hungry beast lurking beneath. Most galaxies, including our very own Milky Way, are believed to harbor supermassive black holes at their very cores. These behemoths, millions or even billions of times the mass of our Sun, rule their galactic kingdoms with an iron fist. Their immense gravity bends the surrounding space-time, influencing the orbits of stars and gas like cosmic marionettes. By mapping these orbital motions, astronomers can trace the invisible hand of the galactic ruler, black holes. In 2015, the universe sang a new song. Gravitational waves, ripples in the fabric of space-time predicted by Einstein, were directly detected for the first time. These cosmic tremors were produced by the violent collision of two black holes, a direct confirmation of their existence and a glimpse into their mind-bending power. So, where do white holes come in? Ah yes, white holes. The same thing as donut holes, right? The enigmatic counterparts of black holes in the realm of theoretical physics. Unlike their light-gubbing brethren, white holes are hypothesized to spew forth matter and energy, acting like cosmic fountains in the vast expanse of space. But are they a reality or just a figment of our scientific imagination? Our current understanding of white holes stems from Einstein's theory of general relativity, which suggests that for every black hole, there might be a corresponding white hole in a different region of space-time, connected through a tunnel called a wormhole. However, unlike black holes, which have been indirectly observed through their gravitational influence, white holes remain purely theoretical. So why so elusive? One major hurdle in verifying white holes is their theorized behavior. According to their mathematical description, anything approaching a white hole's event horizon, the boundary beyond which nothing, not even light, can escape, would be ejected outward at speeds exceeding the speed of light, a physical impossibility within our current understanding of the universe. Additionally, the immense energy spewing from a white hole would make it incredibly hostile, rendering direct observation extremely challenging if not impossible. So, let's look beyond the black and white. Despite the lack of concrete evidence, the concept of white holes continues to intrigue scientists. Some theories propose that white holes could have played a role in the Big Bang, spewing forth the initial burst of energy that gave birth to our universe. Others suggest they might exist in exotic regions of space-time, like the very early universe, or within black holes themselves, acting as a sort of cosmic drain plug. But the universe is full of possibilities. Predicting the future of scientific understanding is like gazing into a cosmic black hole itself, full of possibilities, but shrouded in unknowns. However, considering current research and ongoing debates, here is a contender for a future alternative to the black hole concept: quantum fuzzballs. Imagine, instead of a point-like singularity with infinite density, a black hole as a dense but finite ball of swirling threads made of exotic quantum particles. This hypothesis is known as the black hole fuzzball, and it presents a fascinating alternative with intriguing evidence. Advanced mathematical models based on string theory suggest these dense threads, woven from hypothetical preons, could create the immense mass and gravity of black holes, offering a structure beyond just a singularity. Fuzzball models predict specific entropy values for black holes based on their quantum threads, aligning surprisingly well with observations of their evaporation, Hawking radiation. This adds weight to the idea that their internal structure plays a role in their behavior. Research is still ongoing, but the fuzzball concept offers several advantages. It resolves the singularity problem. One of the biggest challenges with the traditional black hole picture is the concept of a singularity, a point of infinite density at the center. This poses a mathematical problem within quantum mechanics, and it raises questions about how information gets preserved when matter falls in. The fuzzball avoids this issue by proposing a finite, albeit still incredibly dense interior made of quantum threads. This potentially eliminates the singularity and its associated theoretical headaches. The fuzzball concept fits well with promising theories like string theory, aligning with quantum mechanics. The fuzzball concept, being rooted in string theory, naturally incorporates quantum principles. This offers a more harmonious picture of how black holes operate within the framework of quantum mechanics. In contrast, the singularity in a traditional black hole presents a conflict with quantum principles due to its extreme conditions. Hawking radiation, the theoretical slow evaporation of black holes, can be elegantly explained in the fuzzball context. Models suggest that the internal structure of the fuzzball plays a role in this process, providing a more detailed understanding of how and why black holes radiate. Information is encrypted, not erased. The holographic principle proposes that the information about a three-dimensional object can be encoded on its two-dimensional boundary. The fuzzball hypothesis aligns with this concept by suggesting that the information about matter falling into a black hole is actually stored on its event horizon, not lost beyond it. This resolves the information loss paradox, a major concern in the black hole model. So what does it all mean if the fuzzball hypothesis was proven to be accurate? The biggest impact would be on the nature of black holes themselves. Abandoning the singularity concept implies no big crunch scenario, the idea that the universe collapses back into a singularity at the end. The fuzzball's alignment with string theory and quantum mechanics offers a potential bridge between those two fundamental frameworks. If it's proven, it would provide significant evidence for the viability of string theory and its quest to unify gravity and quantum mechanics. It would revolutionize our understanding of the universe at its most fundamental levels. Instead of an inaccessible singularity, the fuzzball paints a picture of a dense, intricate internal structure made of quantum threads. This opens up exciting possibilities for future research, potentially allowing us to probe the black hole interior through its event horizon and understand its behavior on a finer scale. Our understanding of how black holes form and evolve might need some revision. The fuzzball hypothesis suggests that they could arise from dense concentrations of preons, potentially leading to new predictions about their distribution and behavior throughout the universe. If fuzzballs are connected to string theory, it could influence our understanding of the Big Bang and the early universe. String theory suggests additional spatial dimensions, and the fuzzball concept might provide insights into how these dimensions manifested in the early universe and influenced its evolution. While both black holes and their fuzzy adversaries lack direct observational confirmation, the fuzzball hypothesis offers some potential avenues for future testing. For example, certain predictions about specific features of the event horizon or the behavior of evaporating black holes could be tested with advanced gravitational wave detectors. This provides a path for future research and to potentially distinguish between the two models. At the same time, it is important to remember fuzzballs are still under development. They haven't reached the same level of established evidence as the black hole model. Preons remain hypothetical. While the mathematics work, the existence of these fundamental particles needs more experimental confirmation. The fuzzball's interior structure and its connection to the event horizon also raise some new questions that need further investigation. Ultimately, whether the fuzzball dethrones the black hole as the king depends on future discovery. Both concepts enrich our understanding of the cosmos, driving progress and reminding us that the universe's deepest mysteries often hold the key to unlocking even greater knowledge. So, keep your eyes on the cosmic horizon as the next revelation unfolds. Thanks for watching.